one's called. Chapter 3A, sections 3.1 to 3.5. The test that we're trying to have next Friday is all about graphs. Okay, section 3.1, extrema. What's extrema mean? Extremes, maximums and minimums. What are the two different types of extremes? Absolute, and there's two different words for it, relative or general, kind of local, like local vicinity, right? Absolute extrema can happen at either
endpoints or critical numbers.
Endpoints or critical numbers, good. What are critical numbers?
The zero does not exist.
When the derivative is either equal to 0 or does not exist. Good. When the slope, which is the derivative, is equal to 0 or does not exist. Endpoints, they're just given to us, right? No big deal. What theorem is it that says that if a function is continuous? What is it? Oh, mean value. Hold on, that's section 3.2. Too soon. Go back. Extremes. What's that theorem with extremes? Good. If a function is continuous on a closed interval, then it must have
Extrema.
an absolute. Not just any extrema, but an absolute min and an absolute max. We don't know about relative. Maybe not. But an absolute min, absolute max, and they'll either happen with critical numbers or with endpoints. Okay, 3.2. 3.2. Mean value theorem. What was the other one? The special one. Rolls. Roll flat, right? Okay. So the special one, rolls. Well, both of them. The function has to be continuous on a closed interval, filled in at the endpoints. Has to be differentiable on the open interval. No sharp points or vertical tangent lines in between. Mean value theorem says, cool, if those two things are true, then I can tell you there exists at least one C inside A to B, such that
It's equal to the average.
the instantaneous equals the average, or the derivative equals, what's the average formula? Zeros for rolls. Hold on.
F of B minus F of A all over B minus A.
Okay, so mean value, the general one, the one that encapsulates rolls but was discovered later, says there must be a place where the derivative f prime of C, find the C, equals f of B minus f of A all over B minus A. Rolls says, hey, I can tell you the derivative must equal 0 as long as what third condition is met?
F of B equals
F of A equals F of B. That's the Rolls theorem. Okay? That's mean value theorem. You're dabbing it back there? Okay. That's Rolls and mean value theorem. Okay? Now we come to section 3.3. We say, okay, what's something else that we can talk about with a graph and with this behavior? We can talk about when it goes up and when it goes down from a function without having a graph. When it goes up and when it comes down without having a graph. And all of that depends on, well, a function will be increasing if its second y value is higher than its first y value, right? So if the y values are getting higher, then we can say it's increasing. If the y values are getting lower, we can say it's decreasing. That's cool and all, but how can we tell that from a function?
Absolutely no idea.
Plug in some numbers.
We could plug in like all kinds of x's and say, hey, are the y's going up or down? But what if like in the decimally part, what if we plug in this and what if we plug in that and say, oh, it's higher, but what if it does that in between? Well, that doesn't work.
Plug in more numbers.
Okay, so we can plug in infinitely many numbers or just say, hey, I wonder what the slope is. And if the slope is positive, the derivative, good. If the slope is positive, guess what that means about the function? It's pushing up. If the slope is negative, guess what's going on?
Down, pushing.
Exactly. So let's talk about that.
Oh.
Let's talk about that. Let's get back to that in a second. I'll be an example. Here we go. Before we talk about a nasty graph like the one you just saw, I'm going to actually move that through in a different order. Let's first talk about, okay, what if a graph is super boring? Okay, if a movie wants to make a teacher super boring, what do they do to the teacher's voice?
They make it monotone.
Exactly. Strictly monotonic. If they want to make a teacher super boring to prove a point in some sort of movie, they can make him monotone. Or have him or her be monotone. What? What'd you say?
Is it better to have a teacher in mind?
Oh dear. That's scary.
You know what I'm talking about.
Uh-oh.
Do I? I don't know, I feel like you do.
Don't.
Okay, so if they want to make a teacher boring, they make him monotone. Why? Because monotone only has one pitch, only has one level. They're just talking like this the entire time. Oh my goodness, all right, today, guys, we're gonna learn this, and oh my goodness, this is so exciting.
It
Okay.
works better with the guy.
What?
It works better with the guy teacher.
Oh yeah, it definitely works better with a guy teacher. Like the dry eyes guy.
Absolutely.
What's that? The dry eyes? Is that like the actual brand? Oh, is that? Are those commercials on? I don't know.
Oh, like Humira, chronic dry eye.
Yeah.
I have chronic dry eye. That lady doctor.
Oh no, I was talking about the guy. There's a guy with glasses, and he's just like, "If your eyes are dry eyes." I don't know. It's from a while ago. Never mind. Anyway. Monotonic, it's only doing one thing, so super boring graphs are only going to increase or only going to decrease. They're not really that boring, but the boring ones are the easier ones to graph. They're strictly monotonic. Okay, a function could be just increasing or just decreasing. And if it was just increasing or just decreasing, then the derivative sign is always positive or always negative. It can't be always zero, because if the derivative sign is zero, what's that graph? Flat. Yeah, so it's not doing anything, it's just chilling. It's constant is what we would call it. Oh yeah, derivative of any constant is zero. All these words coming together. If it's just increasing or just decreasing, then the derivative sign is either always positive or always negative. Now there was a note at the bottom. That's a good note, we'll get back to that. But can anybody think of an example of a function that only increases or only decreases?
Like a line.
Y equals x? Sure. So if we were to say f of x equals x, kiddos, how would his derivative tell me he's only increasing? We know what he looks like, he's one that we know, but
The derivative is 1.
his derivative would be
So it's always in.
1, which is always positive, which means it's always pushing up. Can anybody think of one that's a little bit more involved?
LN?
Oh, okay, we could do another graph, but let's think of another type. Let's think of ln, that's a good example. ln of x. Okay, ln of x. Now hold on. We know what ln of x looks like, right? He is strictly increasing, but here's the confusing part. Who's his derivative?
Oh, weird.
1 over x.
Like a
Couldn't 1 over x be positive if x is positive, negative if x is negative?
Domain problem.
Exactly. What's the domain of ln of x, guys? Isn't there a vertical asymptote? X has to be
Greater than 0.
greater than 0. So if we remember that the derivative of ln is only true for x greater than 0, then can't we say it's always positive? Okay, so that's one that's a little bit more hidden, where the derivative could be positive, could be negative, but
it's on the other side, it's decreasing, but that's when it's.
the other side, it doesn't exist in ln, so there are no slopes for me to even think about. Okay, at the very bottom it says, all right. So we talked about these boring ones that only increase or only decreasing as seen by the derivative sign only being positive or only being negative. But then it says if a function is not strictly monotonic, when can it change?
Critical point.
Critical points. Why? If the function is, no. If the derivative is positive, what's the function doing?
It's
Increasing.
getting closer and closer to 0.
If the function's positive, or the derivative is positive, pushing up, right? It's increasing. If the derivative is negative, it's
Decreasing.
decreasing. Well, how can a function change from increasing to decreasing? Well, how can a derivative change from positive to negative? IBT. What has to be in between a positive and a negative?
A 0.
A 0. And what's a 0 of a derivative?
A critical number.
So therefore, we get to, oops, wrong direction. Boop, boop.
Ooh, one more.
Ugh.
Back.
Oh, I skipped it. I was like, wait, I thought it was right there. Increasing, decreasing test for functions. Dun, 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 dun. Even though you guys basically discovered it if you thought about it carefully. If the derivative is greater than 0, then the function is increasing. If the derivative is less than 0, then the function is decreasing. I'm actually going to change this because a college professor kind of ragged on my forever card to poor Bridget Marquette this year. I was like, your teacher didn't know what they were talking about. Okay. I put this third one saying if the derivative is 0, I have to add to this just a little bit. On an interval, then the function is constant. The teacher got mad because technically if it's just 0 for an instant, for an x value, it is not a constant function because it's not constant for a whole interval of time. It's constant in one sliver, which is like a momentary stop, which is like a ball going up and coming down, and it momentarily stops at the very, very top. But we don't call that constant because it's not for any time interval. It's for an instant that has no length in and of itself. Anyway, long story short. If f prime is positive, then f is increasing. If f prime is negative, then f is decreasing.
This is a forever card.
If f prime is 0 on an interval, then f is constant. Yeah.
That's what we gotta do, you know.
Okay.
Like, number, just like,
You're on 16.
What's it called? Increasing the decreasing thing.
No, I'll just leave it the way it is. I'll just leave it the way it is. It's called the increasing decreasing test because it's like, how do you know when a quantity is increasing or decreasing? You must look at his derivative signs. It's called the increasing decreasing test because to know whether a function or a quantity is increasing or decreasing, you must check its derivatives signs. So we're talking about discontinuities and how that could be a problem depending on the situation. Just real quick review. If we have an f over a g, well, you guys help me out. You don't need me to do this. What are some other times when the domain is restricted besides a fraction? Square root of any sort of log. I'll just put ln, but it could have been any log, right?
Absolute.
No, absolute value. The derivative might have problems, but the original one.
What about like,
We could do piecewise, but that's hard to write about. You have to check the separator and see if they match up. I'm going to do the last one. I'll just do an example. Can I just put tangent, for instance? Sorry, this is the one that's in cursive and the rest aren't. That's a little awkward.
Side.
No, sine is continuous everywhere, so is cosine, but all the rest have vertical asymptotes. So I just put tangent as the example. Remember, for a denominator, g can't be 0. For a square root, what's inside has to be greater than or equal to 0. For a log, what's inside just greater than 0. And then for tangent and the other trig, basically they can't equal the vertical asymptotes, which for tangent would be plus or minus pi over 2 and beyond, but the trig doesn't really show up all that often. So guys, this is pre-cal review. I just figured since I'm saying watch out for discontinuities, let me remind you of when the domain is restricted. Okay? With that, I'm going to go ahead and dual page it. A couple of you guys are still writing. That is forever number 23.
Wait, is that for f of x? Is that f of x is greater than 0?
Oh, for the square root, it's greater than or equal to.
Oh, greater than.
For log, it's greater than. Yeah, log has a vertical asymptote we have to be aware of. Square root does not. Okay, so with that, I want you guys to look at the following, okay? When would you say this function is increasing? And remember, for increasing, decreasing, they're x intervals. We're moving left to right and saying, okay, how far left, how far right are each of these intervals? It could be more than one. Where would you guys say this function?
So from negative infinity to
Okay.
1.
Because it keeps going this way. We'll just put little arrows on the ends. There's no endpoints marked. So from negative infinity to 1, it's doing what? Good.
Open interval 1.
Why does there need to be an open interval at 1? With a vertical asymptote. Good. So it's decreasing all the way up to 1, but not that one. Where else is it decreasing?
Same thing, 1 to closed interval and 1 to 4.
Because you have to jump the 1 because it's a vertical asymptote, but from 1 to 4, yeah, it's also going down. Now problem, what's going on at 4?
Critical.
Sharp point, which means the derivative, oh, so it's not any of those.
No.
Okay, so we're just gonna leave the 4 off also. Since the derivative at 4 is not negative or positive, it does not exist, we can't say it's increasing or decreasing, we can't include it. So we have to keep him open also. It's decreasing again starting at 5, yeah? 5 all the way to 6. So where is it increasing?
4 to 1.
Good, 4 to 5. Now, hold on, are we gonna include 5 or not include 5? What's the slope of the tangent line at the smooth turn? 0. But is that increasing or decreasing? No. So we're gonna go, here's where the college professor would get mad at me. At 5, the graph is not constant.
So you just
The derivative is 0, which means it's momentarily stopped, but it's not constant for an interval, so we don't actually call it constant. But we can say it's momentarily stopped, or we can say it's in between the increase and the decrease.
So how would you write it?
Just leave it off, open interval, because we can't include it in this or in that. It's also increasing from, what is that, 6? 6 to infinity. Okay, now here's the dealio. Here's where we're going to get to. We're going to get to, basically, not knowing what the graph looks like, having the original function, and what we want in order to be able to figure out more about the graph. Well, we would have to have found 1, 4, 5, and 6. We're going to figure out how to make a sign chart where we look at the signs, or I should say the sign of f prime. And it's going to tell us about the behavior, I said that weird, sorry, of f. Behavior of f. This is what we call a sign chart. And I'm going to actually give you guys words and steps about how to think about a sign chart. But kiddos, let's just think of it. What if we didn't have the graph at all? What could we do mathematically to find 1 and 4 and 5 and 6 from the function?
Critical numbers.
Critical numbers, wait, that would be 4. That'd be a DNE, right? So that's a crit number. And that's technically a DNE.
They should have crit.
Does that mean something that I don't know?
Bloods and crips. They're gangs. I don't know.
I don't want to know.
You mean like crit? No, you mean crit. There's something
You know
about it.
crip?
Crip.
Bloods and crips. It's irrelevant. It's
Is
irrelevant.
that from West Side Story?
No. No, it's real. They're real
So
gangs.
this is real life.
Tupac was a crip.
Okay, what's going on in this one? This is throwing me off.
A 0.
It's a 0, so it's a crit number. This is not a gang. That'd be a 0. And then what's going on at 6?
It's a blood number.
I think that's a sharp point, right? Is that smooth or sharp?
It was sharp.
Looks sharp to me too. Okay, so that'd be a...
Because the other one's a constant increase.
Oh, that's true.
I've exposed myself to all
Thanks for enlightening me, guys. Thank you.
Good.
Sarah's going to add that to her review poem. Okay, so... But 0 did not look like a 0. But how will we get 1? He's not a critical number. He's a discontinuity, right?
Wait, which one?
Isn't he a domain problem? 1. Because the derivative does not exist at 1, but we wouldn't have found him from finding horizontal, vertical, DNE, tangent lines. We would have had to find him from the domain. And then, kiddos, look at this. What was the function doing all the way to the left of this discontinuity? What was it doing this whole time?
Decrease.
Yeah. Because there is no opportunity for it to switch. Whatever it's doing, strictly monotonic, super boring. Whatever it's doing, it's going to have to keep doing because there are no other discontinuities or critical numbers. So the nice thing is on a number line, all I have to do is pick one number, like 0 or -1 or -2, and all I have to do is plug it into the f prime, and once I figured out that one of them is negative, all of them are negative for that entire interval. So that entire time, just by plugging in one value to the left of -1 into the derivative, I could say that whole time it's decreasing. In between 1 and 4, since there are no critical numbers, since there are no discontinuities, I can say plug in anything, 2 or 3 or 1.5 or 2.99999, whoever or whatever their derivative is. That sign tells me what that function's doing the entire time. Yeah.
So would this graph be a piecewise?
Yeah, because it has like a parabola-ish and it has the this and the that. So it would actually probably have its domain split up into different intervals.
So when you're finding like the f prime, don't you have to find it for like both?
You would have to plug it into the right pieces derivative. But you would know because the 2 would have been only in one little x interval. What would happen if we plugged in something between 4 and 5? Well, that'd be nasty. 4.1, 4.5, 4.9. Whatever we plugged in though, what would the derivative be? Positive, because it's increasing. And so all of those are going to behave or show the same behavior. What's going to be going on between 5 and 6? One of them, and so all of them will be negative. I only need to test one though. And what's going on from 6 to infinity? One of them or all of them are going to be. Now, this doesn't give me the exact graph. We're not to section 3.5 yet. But does it give me, it's going down, it's going down, it's going up, it's going down, it's going up? Yeah. It gives me the behavior. But did I have to test infinitely many points and figure out all the y's, whether they're higher or lower? No. I just had to test one in each interval, but how did I split up my number line? Critical numbers and the zeros and DNEs and domain. So kiddos, guess what? That's this entire page, but let me zoom in on it. This is how we're going to analyze a function for increasing and decreasing. And to be honest, oh, I have no idea what just happened. Oh yeah, I do. I skipped a page. This is how we're going to analyze a function for increasing, decreasing. But basically, you guys just kind of discovered the whole process on that example of the page before. Yes, I helped a little bit, but
You did the entire thing.
but hopefully I showed you why.
The CDF light out.
I think so. Steps for analyzing for increasing, decreasing.
Is this similar for every club?
No,
Oh, thank
no. I don't necessarily want you guys to memorize it word for word, but I do want you to know all the steps. It's important to realize the very first thing we have to do is check for discontinuities. Like that one on the page before. Sometimes they show up in critical numbers also. We must check for discontinuities. Hence the domain problems. Check domain. Solve for the first derivative and find the critical numbers, where f prime equals zeros or is undefined. Where f prime has zeros or is undefined. Remember, not every derivative is undefined, so we don't always have to worry about that. Technically, not every derivative has zeros, but we have to check. And this third one, the sign chart, just think number line. It's a snazzy number line. Where you put down the numbers that you found from numbers 1 and 2. Put down any discontinuities, put down any critical numbers. Test a point for each interval into the first derivative, checking the sign. We only need to check one. Before we did that example, you guys were like, okay, let's plug in infinitely many numbers. That sounded awful. If we separate our number line based on the discontinuities and the critical numbers, no big deal. All you have to do is check one, because of IVT, if there are no critical numbers or discontinuities, the derivative must be strictly monotonic in that interval, must be doing the same thing. So check one, and you're done. Check one, and you got it. And then sketch the conclusion for the original function's behavior. Right now, we're just going to sketch with straight lines, going up or going down. Once we get to section 3.4, we can check concavity. And so we can know not only is it going up, but is it going up in a concave up fashion, like a smile, or is it going up in a concave down fashion? And just imagine, that will definitely add to our ability of graphing. But right now, all we're gonna do is just straight line up or straight line down, because we haven't talked about concavity, and we can't really talk about it until we finish this section first. Okay? So then tomorrow, what are we gonna do? We're gonna go ahead and take a function that we don't know the graph of. Now maybe you could kind of guess on it. We're going to test increasing, decreasing for a few different functions. But then we're going to say, wait a minute, how do we use this increasing, decreasing things to find relative means and maxes? All right, cool kids, great job today. You can definitely start on homework with increasing, decreasing. But if it says anything about relative extrema, pause and wait. It is chapel day.
Put in 2 minutes.
Okay.